On slide 8, I turn to the main topic of multi-step LTA, where we add distal outcomes and covariates to the basic LTA measurement model, with a special feature that we're going to consider missing data on the covariates. And we're going to talk about 3 different methods in the context of using imputation for the covariates with missing data. Slide 9 shows the model. So we have the 6 latent class indicators at time 1 and the 6 indicators at time 2. And now we add a set of distal outcomes out here, y, and we also add a set of covariates, x, down here. So we have a combination of different kinds of covariates. x1 is binary, x2 through x3 are continuous, and we have missing data on x1 and x2, but not on x3. The distal outcomes are also of different kinds. y1 is binary, y2 is ordinal, and y3 is continuous. And we have no missing data on these y's for simplicity here. And note that we specified that it's C2 that influences the distal outcomes, not C1, nor a combination of C1 and C2 influencing the y's. We're going to talk about those topics towards the end of this web talk. But it's natural to think that the last time point of the LTA is what's relevant for predicting a distal outcome. Now note also that there's no interaction between C1 and X in their influence on C2. So you can portray this as the influence of X on C2 does not vary across the C1 classes. And in Webtalk 2, where we talk about LTA, in the non-multi-step approach, we refer to that as the main effect model. No interaction between C1 and X in the influencing C2. Main effect model as opposed to the interaction model. And I would argue that in most cases the main effect model is sufficient. I see many applications from Mplus users with the interaction, and perhaps we're guilty because our users guide examples featured such interactions, but we just wanted to show the full generality, not necessarily what we recommend in any given application. So now note also that C2 and X do not interact in their influence on the y's. So the regression of y on X is not C2 specific. So that's what we talked about in Webtalk 8 for latent class analysis. So you just consider this part of the model down here, well, with the indicators too. So there's no interaction between, in the influence of X on Y, it's not C2 specific, but there's only a main effect of C2 on Y and an main effect from X to Y as well. Now the measurement model is what we refer to as this part. So we have 12 indicators total of 2 latent class variables. And now we're going to add to that measurement model the distal outcomes and the covariates. So the multi-step idea here is that the covariates and the distal outcomes should not affect the measurement part of the model, should not affect the formation of these 2 latent class variables. And we talked about the multi-step rationale in Webtalk 8 about LCA with a single latent class variable, claiming that there is a need to separate the estimation of the measurement model from the full model adding then the distals and the covariates, so the latent classes don't change. And that's with respect to both distal outcomes and covariates. Distal outcomes in the full model, that is adding the y's after time point 2 in this case, they may be measured later in time than the variables of the measurement model. And you want to predict from a measurement model using the information you have at that time point. And the covariates in the full model may also affect the latent class enumeration. And if you go back and forth between different set of covariates, you would have to, in principle, redo the latent class enumeration. So you want to separate the estimation of the measurement model from the full model. And that is what's done by multi-step approaches. The first step, the latent classes are determined only by the measurement model. And the last step, distal outcomes and or covariates of the full model are added. And the theory for this multi-step approach is described in the statistics methodology section of Webtalk 8 on LTA. Now we're going to talk about three approaches: 3-step, BCH, and 2-step. And for 3-step, we're talking about what's sometimes referred to as maximum likelihood 3-step. BCH in some literature is also referred to as 3-step, but we think of that only simply as BCH. So 3-step and the BCH approaches use the posterior probabilities from the estimated measurement model to determine each individual's most likely class membership and take its measurement error into account. And we describe that in detail in Webtalk 8. So in 3-step, the last step then uses fixed loaded values from the measurement model to take measurement error into account in the most likely class classification. For BCH instead, we use weights from the measurement model to take measurement error into account in this most likely class classification. 2-step takes a quite different approach. Last step uses fixed measurement model parameters to avoid measurement error in this last step. So that's an interesting newcomer to the methods arsenal. Slide 12 then. What about studies of multi-step approaches for LTA? Well, surprisingly, there are rather few, it seems. I may be overlooking some papers or some recent results. But there are simulations in our web note 15 and 21 that Timur Asparahov and I did. And we looked at covariate setting for LTA 3-step in web note 15. Seemed to work okay. And BCH was looked at for covariates in web note 21. Also looked okay. For distal outcomes, we looked at simulations for BCH in web note 21. And we find that BCH does better than 2-step when distal outcomes are non-normal within class. But there's so much more that could be studied here for multi-step LTA. And note then, if you're interested in that 2-step is harder to study, as it says here, because logistically, for each replication, the parameter values need to be changed. Now we're going to take a look at the special case of this, where you have missing data on the covariates used in the last step analysis. And that's where imputation comes into play, as I was mentioning. On slide 13, I list the various multi-step approaches that you can use with missing data on X in the last step analysis. You can bring covariates into the model, or you can do multiple imputation. Those are the two main approaches. Bringing them into the model, which is explained in detail in Webtalk 8, can use either maximum likelihood or Bayes. With maximum likelihood, you need to do numerical integration, and you can use 3-step for that. BCH is not available with numerical integration in this last step. It is available in the first step, as we will see towards the end of this talk when we talk about RI LTA, random intercept LTA. 2-step works as well. So the advantage here of ML is, of course, that we have likelihood ratio testing. And then the disadvantage is that you have a hard time handling many covariates with missing. It can be somewhat unstable with large amounts of missing data, and can be imprecise without many integration points. And we cannot specify that the covariates are categorical when that is the case. Remember the binary x1 variable. Alternatively, instead of ML, you can use base, you can use 3-step. You cannot use BCH because that's not available due to the weights. We don't have weights in base. And you can also use 2-step. The advantage is it's stable, perhaps more so than the ML. And the disadvantage is no likelihood ratio testing. Can be slow, cannot specify categorical covariates either. We're going to focus on the alternative of multiple imputation of the covariates X in the last step analysis. And in that case, we have all three methods available. And the advantage is that that's a stable analysis. You can specify categorical covariates, and you can also use non-model variables for missing data imputation. That is, variables that are not part of the model but nevertheless can be contributing useful information for the missing data imputation. And the disadvantage is then that we don't have the likelihood ratio testing worked out for the multiple imputation approach, and it can be slow with many covariates that have missing. So if you don't have a lot of missing, you may not want to get into these methods at all. Now, the corresponding LTA approaches were discussed in Mplus Webtalk 8. So now, one comment here regarding BCH on slide 14 to pay attention to. The BCH weight computations in the first step require attention. Webtalk 8 discusses BCH weights for LTA with one latent class variable, that is. Now for LTA, you get the BCH weights as the product of weights for each time point, as if you were estimating them separately. Now we don't have to estimate them separately. We can do a joint analysis of all time points and obtain a separation of the time points in the estimation by not regressing C on C, that is C2 on C1 in this case. Because then the weights for each time point can be automatically or are automatically multiplied together to create weights for all time points. So you do an analysis of time 1 and time 2, U1 through U12, and you get the weights automatically created in the right way if you do not have C2 on C1. So in the first step analysis, you do not include C on C, but in the last step you do. And in Web Note 21, Tiermer did some nice simulation studies to see that that's the way to go. The first step and the last step, handling of C on C. And this idea of not including and including agrees with this paper by Susa Back, Teckley, and Vermont from 2013 on these two pages.